About 252 million years ago, at the end of the Permian, the terrestrial biosphere underwent the greatest biological crisis known. The Permian-Triassic extinction eliminated around 90% of marine species and a similar proportion of terrestrial species, including most of the dominant large synapsids such as gorgonopsids and many dicynodonts. This collapse left ecosystems profoundly impoverished, with truncated trophic chains and a slow recovery during the first millions of years of the Triassic. In that unstable scenario, groups that had previously been secondary had the opportunity to diversify and occupy the vacant niches. Among those emerging groups were the archosaurs, a lineage of diapsids that would become central in the history of terrestrial vertebrates of the Mesozoic. Within Archosauria, two major branches soon arose, the line leading to modern crocodiles and the line that includes dinosaurs and birds. This separation, documented in fossils from the Middle and Late Triassic, reflects anatomical changes in the ankle, in the arrangement of the pelvic bones, and in the structure of the limbs, anticipating different modes of locomotion and lifestyles. During the early and middle Triassic, many archosaurs were medium-sized predators or scavengers that coexisted with the surviving synapsids and other diapsids. The climate remained predominantly warm and arid, with marked seasons and vast interior regions of Pangaea subjected to strong fluctuations in temperature and humidity. In that context, a process of evolutionary experimentation took place. Different lineages tested combinations of size, diet, and posture, and only some of them prospered in the long term. The first representatives close to dinosaurs are found within Avemetatarsalia and are grouped under the term dinosauromorphs. These animals were not yet dinosaurs in the strict sense, but they shared key traits with them. Among the early dinosauromorphs, small and gracile forms have been described with elongated hind limbs adapted for running, such as some lagopetids. Their anatomy suggests agile lifestyles, possibly insectivorous or carnivorous on small prey, occupying intermediate niches in Triassic faunas. Another closely related group, the dinosauriforms, shows a greater degree of convergence with dinosaurs. This category includes animals such as Marsuchus and the Silosaurids, among them Acylosaurus and Silosaurus. The latter display a striking combination of traits, a pelvic girdle and limb proportions approaching the dinosaurian pattern, yet at the same time dental adaptations suggesting herbivorous or omnivorous diets, which challenges the traditional view of exclusively carnivorous proto-dinosaurs. The discovery of Silosaurids in several regions indicates that these evolutionary experiments were not isolated cases. In anatomical terms, dinosauromorphs and dinosauriforms gradually reveal the characteristics that would make dinosaurs a particularly successful group. The posture of the limbs tends to become more erect, with the legs placed directly beneath the body, improving efficiency in walking and running compared with the semi-erect or S-shaped postures of other reptiles. The ankle acquires a more rigid and specialized structure, allowing more stable movements and a more direct transmission of force during locomotion. The pelvic region begins to show modifications in the connection between the femur and the acetabulum, laying the groundwork for the typical dinosaurian articulation. The geographic distribution of these early Avemetatarsalia appears to have been wide, although the fossil record is fragmentary. Remains have been recovered in what are now South America, Africa, and Europe, but in the Triassic, those regions formed part of a single supercontinent, Pangaea, with few physical barriers to the dispersal of terrestrial vertebrates. That continental configuration facilitated the expansion of emerging lineages over great distances, colonizing different environments from arid interior deserts to alluvial plains and coastal zones. Meanwhile, the other major branch of archosaurs, the pseudoseuchians, was also undergoing significant diversification. Some of them developed relatively erect postures and predatory lifestyles, similar to those later associated with theropods, indicating that the erect posture was not an innovation exclusive to the dinosaurian line. Nevertheless, in dinosauromorphs, this posture became integrated with other changes in the axial skeleton, musculature, and limb biomechanics, giving rise to a particularly efficient locomotor system on land. The coexistence of these lineages implied ecological competition. In the ecosystems of the Middle and Late Triassic, the first dinosauromorphs and dinosauriforms shared prey and habitats with large predatory archosaurs, with herbivorous and omnivorous synapsids, and with other reptiles. The evolutionary advantage of avometatarsalia was neither immediate nor absolute. For millions of years, they formed part of mixed faunas in which they were not necessarily the dominant component. Their future success was built upon small accumulated advantages in locomotion, metabolism, and ecological plasticity. The continuous environmental changes of the Triassic also played a role. Volcanic activity, variations in carbon dioxide levels, and the configuration of sedimentary basins generated periods of aridity, episodes of intense rainfall, and fluctuations in the available vegetation. In that framework, lineages with greater capacity for movement, physiological tolerance, and dietary flexibility had higher probabilities of persisting and expanding. Dinosauromorphs fit that profile, combining generally small or medium size with agility and, in some cases, unspecialized diets. The birth of the dinosaurs, late Triassic and initial diversification. When basal avometatarsalia gave way to the first true dinosaurs, the change was not an abrupt leap, but rather the consolidation of a set of anatomical traits that define the clade Dinosauria. Among these traits are a fully erect posture, with the limbs positioned beneath the body, a perforated acetabulum in the pelvis that articulates the femur in a more vertical orientation, modifications to the pelvic and shoulder girdles that enhance locomotion, and specific changes in the skull and vertebrae that optimize musculature and respiration. The result is an animal better adapted to traveling long distances on land, with more efficient biomechanics than many contemporary reptiles. Fossils from the late Triassic, approximately 230 to 210 million years ago, reveal some of the first unequivocal dinosaurs. In what is now South America, small to medium-sized forms with relatively lightweight bodies have been described, representing the earliest theropods and basal sauropodomorphs. These animals shared the landscape with other archosaurs and synapsids, yet already exhibited the locomotor pattern and skeletal organization that would characterize dinosaurs throughout the rest of the Mesozoic. Among the early theropods were medium-sized bipedal carnivores, with skulls equipped with serrated, backward-curving teeth suited for tearing flesh. Their long, strong hind limbs, together with relatively functional forelimbs, suggest active predators capable of hunting small to medium-sized prey. The stiff tail acted as a counterbalance, stabilizing the body during running. Although these Triassic theropods had not yet reached the size of later large predators, they established the basic model that would be repeated and diversified in subsequent lineages. In parallel, the first sauropodomorphs signal a transition toward herbivorous lifestyles. These animals, initially of medium size, combined relatively small skulls with elongated necks and dentition adapted to processing vegetation, though still lacking the extreme specializations of later giant sauropods. In the late Triassic, they were in many cases facultative bipeds. They could move on two legs, but also adopt quadrupedal postures depending on the situation. This locomotor flexibility, together with a plant-based diet, allowed them to exploit plant resources in different vegetation strata. The appearance of ornithischians also dates to this interval, although their early fossil record is more fragmentary and has been the subject of debate. Ornithischians are distinguished by a particular configuration of the hip, with the pubis oriented backward parallel to the ischium, as well as dental and mandibular adaptations consistent with herbivorous or omnivorous diets. The earliest known representatives were relatively small animals, many of them bipedal, occupying niches as small-bodied herbivores or mixed feeders in Triassic ecosystems. The exact origin of this group and its relationship to certain Triassic proto-ornithischians remains an active area of research, but their early presence indicates that from the outset, Dinosauria included several ecologically differentiated lineages. From a faunal perspective, the late Triassic shows highly mixed communities. In the same deposits where early dinosaurs are found, large non-dinosaurian archosaurs such as some predatory pseudosuchians, as well as herbivorous and omnivorous synapsids, also appear. Dinosaurs were not yet the dominant component in all terrestrial ecosystems. Rather, they formed part of a mosaic in which they shared space and resources with other well-established vertebrates. The perception of dinosaur dominance is more characteristic of later stages and does not reflect the complex reality of these first few million years. The anatomical and ecological diversity already observed in the late Triassic suggests that the internal differentiation of Dinosauria occurred relatively rapidly once the basic body plan had been consolidated. Theropods, sauropodomorphs, and ornithischians, although still in primitive forms, displayed distinct evolutionary trajectories, some toward the refinement of active predation, others toward large-scale herbivory, and others toward a variety of feeding strategies based on plants and possibly small invertebrates. This initial diversification allowed the group to explore multiple niches almost from its origin. The environmental context was still marked by the configuration of Pangaea as a nearly continuous supercontinent. Vast fluvial plains, interior deserts, forming mountain ranges and coastal margins offered a wide range of habitats. The climate, mostly warm with pronounced dry and wet seasons, generated variable conditions for vegetation, including areas of open forests, conifers, tree ferns, and floras adapted to aridity. Early dinosaurs, with their efficient locomotion and possibly more active physiology than many contemporary reptiles, benefited from being able to travel great distances in search of food and water. Respiration and metabolism are less visible aspects in the fossil record, but comparisons with modern birds and crocodiles, together with certain features of the vertebrae and ribs, have led to the proposal that dinosaurs may have developed more efficient respiratory systems than other reptiles. Improved pulmonary ventilation combined with an active lifestyle would have provided clear advantages in variable environments, and particularly in climates with high daytime temperatures. Although the details of this aspect remain under study, the general pattern points to animals capable of sustaining prolonged effort. In evolutionary terms, the late Triassic was a period of experimentation for the group. Many early dinosaur lineages left no descendants in the Jurassic and Cretaceous, yet they formed part of the context that enabled the later success of other branches. The fossil record indicates local extinctions and faunal replacements within the lineage itself, reflecting a dynamic process in which new lineages emerged, expanded, and sometimes disappeared over relatively short spans of time. The picture is not one of a linear and uninterrupted ascent, but rather of an early radiation with multiple evolutionary experiments. The rise of the early and middle Jurassic, dinosaurs become dominant. The end of the Triassic was marked by a new mass extinction that coincided with the transition to the Jurassic. Intense volcanic activity associated with the Central Atlantic magmatic province released large volumes of gases, altering the climate and ecosystems. Many groups of non-dinosaurian archosaurs, as well as various synapsids and other reptiles, disappeared or were severely reduced. In contrast, dinosaurs, along with the first mammals and pterosaurs, crossed the Triassic-Jurassic boundary with relatively smaller losses. This asymmetry in extinctions favored the expansion of the surviving lineages. In the first millions of years of the Jurassic, dinosaurs began systematically occupying niches that were previously shared with other reptiles. Records of Hatangian and Sinemurian faunas show terrestrial communities in which dinosaurs are already a majority component among large vertebrates. Medium-sized theropods, basal sauropodomorphs, and early ornithischians appear on various continents, reflecting a wide distribution within the still continuous Pangaea. The observed pattern is a gradual but sustained replacement of former dominant groups by dinosaurs. Early Jurassic theropods maintain the general model established in the late Triassic, but they begin to show internal diversifications. Lineages with more elongated skulls, cranial ornamentation, and variations in dentition suggesting differences in diet and hunting strategy can be distinguished. Some taxa exhibit bony crests and slight modifications in the forelimbs, indicating a process of morphological experimentation that continues throughout the Mesozoic. These theropods take on the role of the main terrestrial predators in many early Jurassic ecosystems. In sauropodomorphs, the early Jurassic represents a transitional phase from medium-sized prosauropods to true sauropods. Forms appear in which the neck becomes even longer, the spine is reinforced, and the limbs adopt proportions and arrangements clearly oriented toward permanent quadrupedalism. The leg musculature reorganizes to support increasing weight, and the vertebrae show cavities and plates that lighten the skeleton without losing strength. This set of transformations will later make the evolution of giant herbivores possible. Ornithischians, in turn, begin to diversify into recognizable lineages, although still in relatively simple forms. Among the thyreophorans, the first representatives appear that will lead to stegosaurs and ankylosaurs, with dermal plates and incipient osteoderms. Early ornithopods are small to medium-sized, mostly bipedal, with dentition adapted for cutting and grinding low-growing vegetation. These forms occupy niches of smaller herbivores in the same landscapes where larger sauropodomorphs exploit higher vegetation layers. The structure of faunas begins to show vertical and horizontal partitioning of resources. The climate of the early Jurassic, although still influenced by the aftermath of the extinction, tends to be wetter and more stable than that of the Triassic. The presence of extensive river systems, floodplains, and forests of conifers, cycads, and tree ferns provides a sufficient plant base to support growing populations of herbivores. The availability of food resources combined with efficient locomotion and probably a relatively active physiology contributes to the success of dinosaurs compared to less adaptable groups. As the early Jurassic progresses toward the middle Jurassic, Pangaea begins to fragment more noticeably. The initial opening of the Atlantic and the formation of inland seas modify climatic patterns and create new coastlines and sedimentary basins. Although the continents still maintain broad connections, regional gradients of temperature and humidity develop. This environmental heterogeneity favors faunal differentiation. Dinosaur lineages adapted to specific conditions tend to diversify and specialize in particular areas. In the Middle Jurassic, the fossil record shows faunas already clearly dominated by dinosaurs across a wide variety of terrestrial environments. Sauropods have consolidated gigantism in several lineages, with massive bodies, long necks, and extensive tails that allow them to cover large areas while feeding. Their tracks and skeletal remains indicate that they were a visible and structuring part of the landscape, modifying vegetation and probably influencing ecosystem dynamics. Larger theropods appear as the main predators, while smaller forms occupy niches as hunters of small prey or scavengers. Ornithischians continue to diversify and begin to show more complex adaptations in dentition and chewing apparatus. Some ornithopods develop dental batteries capable of efficiently processing tougher plant material, allowing them to exploit resources less effectively used by other herbivores. The first well-characterized stegosaurs, with dorsal plates and armed tails, appear on several continents, indicating that dermal defenses have become a stable component of the survival strategy of certain groups. The trophic structure of Middle Jurassic ecosystems reflects this reorganization. Large herbivorous sauropods and ornithischians of various sizes form the basis of terrestrial food webs, while theropods are distributed across different levels as apex predators, mesopredators, and generalists. In the air, diversified pterosaurs exploit aerial and coastal niches, while on the ground, small nocturnal mammals occupy discrete habitats without directly competing with dinosaurs across most ecological scales. Sedimentary and taphonomic evidence points to the existence of varied environments: river plains with braided channel systems, deltas, shallow lakes, and coastal areas subject to tides. In many of these contexts, concentrations of bones, fossilized footprints, and nests have been found, indicating not only the presence but also the abundance of dinosaurs. The track record suggests patterns of group movement in certain sauropods and ornithopods, although detailed behavioral interpretation remains cautious due to the limitations of the evidence. The height of the late Jurassic: giants, predators, and mature ecosystems. During the late Jurassic, approximately 163 to 145 million years ago, dinosaurs reached one of their peaks in diversity and ecological complexity. On several continents, faunal assemblages are documented in which giant herbivores, large carnivores, and a wide range of medium and small forms coexist, creating mature and structured ecosystems. The fossil record from formations such as Morrison in North America, Tendaguru in East Africa, Lourinhã in present-day Portugal, or some complexes in China, provides a detailed window into these communities. The Morrison Formation in western North America is one of the best-studied assemblages. There, large sauropods such as Diplodocus, Apatosaurus, Brachiosaurus, and Camarasaurus have been recovered, whose anatomy illustrates different strategies within herbivorous gigantism. Relatively slender diplodocids with very long tails contrast with brachiosaurids with higher forelimbs, elevated necks, and a posture adapted to exploiting taller vegetation. These differences suggest a niche partitioning based on the height and type of plants consumed, reducing direct competition between species sharing the same space. In the same stratigraphic unit, stegosaurs such as Stegosaurus appear, with well-developed dorsal plates and tail spikes. Their relatively low bodies, less specialized dentition, and possible preference for low-growing vegetation indicate another level of plant resource exploitation. The combination of tall sauropods with more horizontal necks, and ornithischians such as stegosaurs created a mosaic of herbivores that differently affected vegetation structure, from the tops of conifers to the understory of ferns and cycads. The main large predators of the Morrison Formation belong to the Allosaurid group, with Allosaurus being the best-known representative. This relatively large theropod, with a robust skull and powerful hindlimbs, is well documented both by complete skeletons and isolated remains. Its serrated dentition, neck and jaw joints, and inferred musculature point to a predator capable of attacking large prey, including juvenile or subadult sauropods and stegosaurs. The presence of other theropods such as Ceratosaurus and Torvosaurus suggests a predator guild structure in which different species could have occupied slightly different niches, either by size, preferred habitat, or type of prey. At Tendaguru, in present-day Tanzania, the faunal composition shows parallels and differences compared to Morrison. There, large sauropods such as Giraffatitan, traditionally considered a type of Brachiosaurus, and other early titanosauriforms are also found, along with stegosaurs and medium to large-sized theropods. Flora and sediments indicate coastal and continental environments with periods of flooding and exposure, suggesting that these faunas could move between inland plains and coastal areas. The general similarity of structures, such as giant herbivores, armored ornithischians, and large and medium carnivores, reinforces the idea of recurring ecological patterns in different regions during the late Jurassic. Western Europe and certain regions of Asia show faunas with distinct characteristics. In L'Orignan, sauropods, theropods, and stegosaurs have been found that partially resemble those of Morrison but also include particular lineages adapted to local conditions. In China, formations such as Shishugu document Tetanuran theropods, early coelurosaurs, and diverse ornithischians. The progressive fragmentation of Pangaea during the late Jurassic favored the emergence of differentiated faunal provinces. Although the major ecological types were repeated, specific species and some morphological solutions differed in each region. One key aspect of the late Jurassic is the consolidation of gigantism in various sauropod lineages. Skeletons show vertebrae with internal cavities and extensive bony laminae that reduce weight, along with columnar limbs capable of supporting masses exceeding those of any modern terrestrial animal. The structure of the rib cage, the air sac system inferred by analogy with birds, and certain joint details suggest physiological adaptations to maintain efficient ventilation and adequate oxygen flow in large bodies. The success of these giants implies the existence of ecosystems with sufficient plant productivity and climatic stability to sustain large populations. In ornithischians, stegosaurs represent a clearly defined line of thyreophorans with dorsal plates and armed tails, while other groups, such as medium-sized ornithopods, begin to show more advanced adaptations in dentition and jaw structure. Tooth batteries, wear surfaces, and the strength of chewing muscles indicate greater efficiency in processing plant food. These improvements allow exploitation of a wider range of plants, including more fibrous and tough parts. Although hadrosaurs have not yet appeared, the morphological foundations for later masticatory innovations are being laid. The late Jurassic is also relevant for the evolution of coelurosaurian theropods, the group that will later include feathered dinosaurs closely related to birds. Although evidence of feathers is better documented in Jurassic and Cretaceous sites in China, the structures of certain Jurassic theropods already indicate modifications in skin and body covering. In some small lineages, the presence of filaments or protofeathers may have initially served insulating or display functions before taking on an aerodynamic role. Behavioral evidence from this period is more abundant than in earlier stages due to the wealth of tracks, nests, and bone accumulations. In several regions, parallel sauropod tracks have been identified, suggesting group movement, although the precise interpretation, whether they represent structured herd tracks, temporary aggregations, or shared use of routes, remains open. In stegosaurs and other ornithischians, the combination of dermal defenses and possible gregarious behaviors would have contributed to reducing predation risk. In theropods, certain bone accumulations and bite marks provide evidence of scavenging and possible intraspecific interactions, including fights over resources. From an environmental perspective, the late Jurassic is characterized by warm climates with latitudinal gradients, pronounced seasons in some regions, and a wide distribution of coniferous forests, araucarias, ginkgos, cycads, and tree ferns. Fertile soils in river plains and areas near deltas and coasts provide favorable conditions for vegetation. The combination of temperate to subtropical climates and high primary productivity facilitates the maintenance of communities with very large herbivores and specialized predators. Early Cretaceous, explosion of lineages and feather revolution. At the beginning of the Cretaceous, about 145 million years ago, the fragmentation of Pangaea was no longer just an incipient process, but a geographic reality with clear consequences for the distribution of dinosaurs. The northern continents, Laurasia, and the southern continents, Gondwana, began to separate effectively, oceanic basins opened, and inland seas appeared, creating barriers to dispersal. This configuration favored the formation of differentiated faunal provinces, where related lineages evolved separately and gave rise to distinctive sets of species. In this context, dinosaurs not only maintained their dominant position among terrestrial vertebrates but also underwent a new phase of diversification. Many groups that had been relatively homogeneous in the late Jurassic now branched into specialized lineages. The early Cretaceous is therefore characterized by the consolidation of large clades within Saurischia and Ornithischia, and by the appearance of morphological innovations with profound implications, including the expansion of complex feathers and the development of more diverse birds. Among ornithischians, the thyreophorans evolved into two clearly distinct lines, stegosaurs and ankylosaurs. The former, very characteristic of the Jurassic, reduced their relative diversity in the early Cretaceous, although they remained present in some regions. In contrast, ankylosaurs began a remarkable expansion. Their dermal armor became more complete, with plates and osteoderms covering much of the body, and in certain lineages terminal bony clubs appeared on the tail. These structures, together with a low, robust posture, constituted an effective defense system against large predators. Another branch of the ornithischians, the ornithopods, began to show remarkable variation in forms. Small and medium-sized ornithopods gradually transformed into lineages capable of forming complex dental batteries and efficiently processing vegetation. It is during this period that advanced ornithopods are documented, which anticipate the hadrosaurs of the late Cretaceous, with powerful jaws, continuous tooth replacement, and adaptations for feeding on tougher plants. At the same time, the first basal ceratopsians, small and lacking the later extreme developments of frills and horns, appear in East Asia, indicating the early origin of a lineage that would later be very successful in Laurasia. In Saurischia, the situation is equally dynamic. Among the sauropodomorphs, the early Cretaceous marks the beginning of the prominence of titanosaurs, a group that includes the future southern hemisphere titanosaurs and long-necked forms that gradually replace many typical Jurassic sauropods. These animals retain gigantism, but show variations in the shape of the vertebrae, pelvis, and limbs, indicating adaptations to different types of terrain and vegetation. In Gondwana, in particular, titanosaurs will become the dominant large herbivores. Among theropods, there is a marked diversification of coelurosaurs, the group that will eventually include birds. In the early Cretaceous, primitive tyrannosauroids are already recognized, of moderate size and with proportions different from later large tyrannosaurids. Early therizinosaurs with elongated claws and adaptations to omnivorous or herbivorous diets, oviraptorosaurs with short skulls and, in some cases, toothless beaks, and dromaeosaurids developing stiff tails and long feathers on arms and tail. This morphological variety reflects a very diverse occupation of niches, ranging from agile predators to potential consumers of plants, eggs, or invertebrates. The expansion of feathers is one of the key phenomena of the early Cretaceous. While simpler forms of dermal filaments probably already existed in Jurassic theropods, in this period more complex structures are documented. Feathers with a defined rachis, barbs, and in some cases aerodynamic asymmetry. In many non-avian coelurosaurs, these feathers likely served for thermal insulation, visual display, and in small forms, assistance in jumping or gliding. Feathers thus become a stable component of the biology of numerous theropods, not restricted solely to birds. The first birds from the early Cretaceous record show rapid diversification. Groups such as enantiornithines, or opposite birds, and early ornithuromorphs display combinations of reptilian and avian traits, still relatively long tails in some forms, functional claws on the hands and teeth in the upper and lower jaws, together with clearly avian elements such as the pygostyle, well-developed flight feathers, and an incipient keel on the sternum. These birds occupy varied niches. Some appear adapted to arboreal environments, others to shallow water zones, and others to more generalist lifestyles. From a paleo-environmental perspective, the early Cretaceous is characterized by generally warm climates, but with more pronounced regional differences than in the Jurassic due to increasing continental separation. Epicontinental seas developed, penetrating into the continents and creating broad coastal plains, deltas, and inland lake systems. Vegetation still included conifers, cycads, and ferns, but towards the end of the period, the first angiosperms, that is, flowering plants, began to appear initially as discrete components of the flora, not yet displacing the dominant groups. This early presence of angiosperms opened new ecological possibilities that would be fully exploited in later times. Faunal differences between Laurasia and Gondwana became more evident. In Laurasia, the combination of advanced ornithopods, basal ceratopsians, ankylosaurs, and a high diversity of coelurosaurs defines the structure of many terrestrial faunas. In Gondwana, in contrast, the records show the growing importance of abelisaurids, predatory theropods with high skulls and reduced arms, herbivorous titanosaurs, and other distinctive lineages. These divergences reflect both geographic barriers and independent evolutionary trajectories of lineages in each hemisphere. Evidence of behavior continues to expand. In the early Cretaceous, nests and dinosaur eggs are documented in various regions, some associated with feathered theropods, others with ornithischians and sauropods. The arrangement of the eggs, nest structures, and associated tracks suggest diverse reproductive strategies, from simple laying on soft substrates to more elaborate structures partially covered by vegetation or sediments. At certain sites, the association of primitive bird skeletons with remains of fish and other aquatic organisms indicates specialized feeding habits. Late Cretaceous, extreme ecosystems and maximum dinosaur diversity. During the late Cretaceous, approximately between 166 million years ago, dinosaurs reached one of their phases of greatest taxonomic diversity and ecological variety. The world had changed significantly compared to the Jurassic. The continents were more separated, sea levels were high, and extensive epicontinental seas covered large areas of the land masses. This scenario created warm climates with little ice at the poles and a wide range of coastal, littoral, and continental habitats in which dinosaurs adapted to very specific niches. In Laurasia, particularly in what is now North America and East Asia, very characteristic faunas developed. In western North America, the presence of the western interior seaway divided the continent into two main landmasses, Laramidia in the west and Appalachia in the east. Laramidia, a relatively narrow strip between the sea and the mountains, hosted very dense dinosaur communities, documented in formations such as Judith River and Hell Creek. In these assemblages, hadrosaurids, ceratopsians, ankylosaurids, and large tyrannosaurid theropods appear along with a variety of smaller forms. Hadrosaurids, or duck-billed dinosaurs, had become the dominant medium and large herbivores in many regions of Laurasia. Their skulls displayed complex dental batteries with hundreds of functional and replacement teeth, capable of processing abrasive plant material with unprecedented efficiency among dinosaurs. Some species developed hollow or solid bony crests on the skull, possibly used for visual and acoustic communication. Their success is linked to the expansion of angiosperms, flowering plants, which during the late Cretaceous became dominant in many terrestrial ecosystems, offering new food resources in the form of tender leaves, fruits, and seeds. Ceratopsians reached their maximum diversity in this same context. In Laramidia, numerous ceratopsid genera are documented, with variations in the shape and ornamentation of the frill, the bony skull shield, and the nasal and supraorbital horns. These structures could combine defensive functions with roles in sexual display and intraspecies recognition. Ceratopsians occupied niches of robust herbivores, probably specialized in exploiting low to medium-height vegetation, complementing the diet of hadrosaurids and reducing direct competition. Ankylosaurids, for their part, continued as medium to large armored herbivores with low bodies, osteoderms covering the back and flanks, and in many cases, powerful tail clubs. These animals represented an extreme defensive strategy against large predators. The coexistence of hadrosaurids, ceratopsians, and ankylosaurids generated a highly structured herbivore community where niche partitioning included differences in browsing height, types of consumed plants, and anti-predator strategies. At the top of the trophic pyramid were tyrannosaurid theropods in North America and Asia. These large carnivores with massive skulls and extremely powerful biting jaws, reduced forelimbs, and robust hindlimbs represent one of the pinnacles of terrestrial predator evolution. Their anatomy indicates the ability to take down large prey and withstand the forces generated during attack and the consumption of meat and bone. The structure of their teeth, with thick crowns and reinforced serrations, suggests a diet that included not only soft tissues but also partial bone crushing. East Asia shows a particularly rich radiation of feathered coelurosaur theropods. Dromaeosaurids, troodontids, and oviraptorosaurs show combinations of traits including stiff tails, elongated arms with developed feathers, specialized skulls, and in some cases probably omnivorous lifestyles. Numerous specimens with preserved plumage are documented in this region, confirming that by the late Cretaceous, feathers were widely distributed among theropods, serving functions ranging from thermal insulation to visual communication and, in birds, active flight. In Gondwana, faunal assemblages differ in composition, reflecting separate evolutionary histories. In South America, Africa, Madagascar, and India, titanosaurs established themselves as the main herbivorous sauropodomorphs. These sauropods, in many cases large in size, show significant variations in body proportions, vertebrae shape, and limb robustness. Some were extremely large and heavy, while others had more slender bodies. Their presence indicates that despite the rise of hadrosaurids and ceratopsians in Laurasia, sauropodomorph gigantism remained a successful solution on southern continents. Among Gondwanan theropods, abelisaurids stand out. Carnivores with tall, ornamented skulls, highly reduced forelimbs, and hindlimbs adapted for running. Their anatomy differs from tyrannosaurids, but they occupied similar ecological roles as apex predators. The coexistence of titanosaurs and abelisaurids in several regions suggests trophic networks in which massive herbivores were potential prey for these specialized carnivores alongside other medium-sized herbivores. The diversification of modern birds also has an important chapter in the late Cretaceous. In addition to basal bird groups, enantiornithines and other lineages not belonging to the crown group of modern birds persisted and diversified. Many of these birds show adaptations to specific habitats, arboreal forms with grasping feet, aquatic birds with modified limbs for swimming or wading, and species with insectivorous or piscivorous habits. The coexistence of several avian lineages, some of which would not survive the Cretaceous-Paleogene boundary, reflects intense evolutionary experimentation in the aerial realm. The physical environment of the late Cretaceous was characterized by high sea levels and warm to temperate climates. The absence of large polar ice caps allowed forests to exist at high latitudes, where dinosaur remains were also found, including hadrosaurids and other herbivores adapted to extreme seasonal light conditions. Vegetation was dominated in many regions by angiosperms, accompanied by conifers and other plant groups. This floristic shift affected food webs, providing new types of food for herbivorous dinosaurs and other vertebrates. Fossil evidence also indicates the existence of complex ecological interactions. Possible migratory patterns of some dinosaurs have been inferred from fossil distribution and specific bone growth characteristics. Microstructural studies of bones suggest growth rhythms that could relate to seasonal changes in resource availability. Additionally, bite marks, healed fractures, and bone deformities document events of predation, intraspecific competition, and accidents occurring during the animals' lives. From dinosaur to bird, anatomical transition and the first Jurassic and Cretaceous birds. The transition of certain theropods to the first birds was not a sudden event, but a gradual process that took place throughout the Middle and Late Jurassic and the early Cretaceous. While previous chapters described the general expansion of dinosaurs in terrestrial ecosystems, in parallel a specific branch of coelurosaurian theropods accumulated anatomical changes that would eventually give rise to birds. This lineage includes dromaeosaurs, troodontids, and the earliest avialans, grouped within Paraves, and is characterized by a progressive refinement of structures necessary for active flight. In basal coelurosaurian theropods, several elements already anticipate the avian condition. A relatively reduced skull size compared to the body, increased cranial capacity, a highly mobile S-shaped neck, elongated forelimbs, and a hand with 3 functional fingers. The fused clavicle forming a furcular or wishbone appears broadly in these groups, providing an elastic element that stores and releases energy during forelimb movements, a function that in birds integrates into the mechanics of wing flapping. The skeleton begins to show cavities associated with air sacs, suggesting a more efficient respiratory system. Feathers, initially in the form of simple filaments or poorly differentiated structures, are documented in non-avian coelurosaurs of the late Jurassic. These filaments are distributed across different parts of the body, and in some lineages form plumes on the arms, tail, or head. Their primary function is interpreted as thermal insulation and visual display, although in small animals they may also have altered air resistance during jumps or descents from heights. Over time, these structures become more complex, forming feathers with raches, barbs, and barbules, some aerodynamically efficient. In this context, Archaeopteryx appears, known from the lithographic limestone deposits of Solnhofen in present-day Germany, dated to the late Jurassic. This animal combines a set of clearly intermediate features. It has teeth in the jaws, a long tail composed of numerous free vertebrae, and hands with well-developed claws, but also well-formed flight feathers on the wings and tail, arranged similarly to modern birds. Asymmetric primary feathers suggest the capacity to generate significant lift, although the exact degree of flight control remains under study. The pelvis already shows a configuration closer to that of birds, and the furcula is present, integrating elements of a skeleton adapted to flapping. The significance of Archaeopteryx lies not only in its status as a transitional form, but also in confirming that many avian features originated in terrestrial theropods before the appearance of fully volant birds. However, it was not the only Jurassic avialan. In late Jurassic and early Cretaceous sites, especially in the fossil-rich formations of the Liaoning province in northeastern China, numerous feathered theropods and early avialans have been described, broadening the picture. These deposits preserve fine details of plumage and soft tissues, allowing precise reconstruction of body coverage and wing anatomy. In dromaeosaurs, such as representatives of the Microraptoria group, long feathers are observed not only on the arms and tail, but also on the hind limbs, creating a 4-winged configuration. This arrangement suggests the use of plumage for gliding or aerodynamic control during descents from trees or heights, supporting the idea that flight in Paravians may have included intermediate stages of arboreal gliding. Small troodontids with slender skulls, large orbits, and fine dentition also display feathers and forelimb proportions, placing them near the base of birds. Early Cretaceous avialans already show a reduction of the bony tail and the formation of a pygostyle, a short structure where tail feathers are attached. This change reduces weight and improves flight control, while allowing a more compact arrangement of the caudal musculature. The sternum begins to develop a prominent keel in some taxa, increasing the surface area for the pectoral muscles responsible for wing flapping. Trunk vertebrae partially fuse, stabilizing the dorsal region, and fusion of forelimb bones begins, culminating in the carpometacarpus of modern birds. Dentition, still present in many Cretaceous birds, is reduced or modified depending on the group. Some forms retain small teeth suited for insectivorous or piscivorous diets, while others develop ornate or robust beaks, indicating the use of keratin as the primary feeding structure. The replacement of teeth with a beak reduces mass at the front of the skull, and may be related to changes in diet, food processing, and flight aerodynamics. During the Cretaceous, two major avian radiations coexist, enantiomorpha and ornithuromorpha. Enantiomorphs, often toothed and with peculiar skeletal features in the shoulder and tarsal joints, diversify into arboreal, aquatic, and possibly terrestrial forms. Their skeletons show adaptations for active flight with well-developed wings and complex flight feathers. Ornithuromorpha include lineages closer to the crown group of modern birds, some already with beaks and limb modifications indicative of specialized lifestyles such as swimming or shallow diving. The emergence of birds adapted to aquatic environments with webbed or modified hind limbs, and birds with long, slender beaks, probably insectivorous or nectarivorous, reflects the colonization of niches combining flight with feeding in highly varied environments. The coexistence of these forms with non-avian dinosaurs in the same deposits indicates that avian radiation did not immediately replace classic theropods but represented a parallel diversification in the aerial environment. Anatomical changes associated with the avian lineage are not limited to the skeleton and feathers. The reorganization of the respiratory system, with air sacs penetrating the bones of the trunk and limbs, allows efficient ventilation through nearly unidirectional airflow in the lungs. Although direct evidence of soft tissues is scarce, the pneumatic structure of the vertebrae and ribs of many feathered theropods and early birds is consistent with this type of system, providing clear advantages in gas exchange and exertion tolerance. The combination of a lightweight yet reinforced skeleton, developed pectoral musculature, and an efficient respiratory system forms the physiological basis for sustained flight. The K/PG impact, the end of non-avian dinosaurs and the survival of the avian lineage. About 66 million years ago, at the end of the Cretaceous, ecosystems that hosted the highest diversity of non-avian dinosaurs faced a sudden disturbance. In the geological record, this moment is marked by a thin layer of sediments known as the Cretaceous-Paleogene boundary, or K/PG boundary, recognizable worldwide for its anomalous iridium content, a rare element in the Earth's crust but relatively abundant in meteorites and asteroids. This geochemical signal formed the basis of the impact hypothesis proposed in the late 20th century and later confirmed by the discovery of the Chicxulub crater, buried beneath the Yucatan Peninsula in present-day Mexico. Studies of the Chicxulub crater indicate that it was generated by the impact of a body about 10 kilometers in diameter, which released energy equivalent to tens of teratons of TNT at the moment of impact. The collision excavated a structure approximately 180 kilometers in diameter, raised a ring system, and ejected large volumes of molten and vaporized material. Part of this material was dispersed globally as microspherules and fine dust, contributing to the formation of the iridium-rich boundary layer. The impact occurred on a carbonate evaporite platform rich in gypsum and other sulfates, favoring the injection of large amounts of sulfur into the atmosphere as aerosols. The environmental consequences unfolded in several phases. In the minutes and hours immediately after the impact, the surrounding area experienced shock waves, high-magnitude earthquakes, and tsunamis that affected continental margins around the Gulf of Mexico and the western Atlantic. On a continental scale, extensive wildfires occurred, fueled by radiated heat and the fall of incandescent material over long distances. Vegetation was severely damaged over wide regions, and terrestrial food chains were almost instantaneously disrupted. On a scale of weeks to years, the dominant effect was the so-called impact winter. Dust, sulfate aerosols, and soot from fires blocked a significant portion of incoming solar radiation, reducing photosynthesis in both terrestrial and marine environments. Climate models suggest a rapid drop in surface temperature and prolonged cold and dark conditions for several years, followed by a longer-term warming period due to the release of carbon dioxide from vaporized carbonates and organic matter. The combination of initial cooling, ocean acidification, and subsequent changes in temperature and water chemistry imposed multiple stresses on many organisms. In parallel with the impact, the planet was experiencing a period of intense volcanism in the region corresponding to present-day India, the Deccan Traps eruptions. These volcanic emissions released large amounts of greenhouse gases, sulfur dioxide, and trace metals such as mercury, contributing to episodes of warming, ocean acidification, and changes in atmospheric circulation before, during, and after the K/PG event. The exact relationship between Deccan activity and the Chicxulub impact remains debated, but most studies agree that both factors interacted in shaping the biological crisis. The result was a mass extinction affecting about 75% of known species, including all non-avian dinosaurs, many groups of marine reptiles, numerous marine invertebrates, and a significant portion of terrestrial plants. Among dinosaurs, hadrosaurs, ceratopsians, ankylosaurs, titanosaurs, tyrannosaurids, abelisaurids, and most non-avian theropods disappeared, as well as several lines of primitive birds, including many enantiornithines and other groups that are not part of the modern bird lineage. The survival of neornithes, the crown group of modern birds, is a central aspect of this transition. Fossil records and phylogenetic studies indicate that some lines of modern birds were already present in the late Cretaceous, although their apparent diversity was lower than that achieved after the extinction. Factors that may have favored the survival of these lines include their relatively small body size, more generalist diets or those based on resources such as seeds and tough plant material, and life habits associated with environments less directly affected by the impact, such as forested inland areas or wetlands. The structure of the respiratory system and flight-related physiology may have provided additional advantages. A highly efficient respiratory apparatus with air sacs and nearly unidirectional ventilation allows better management of low oxygen availability and temperature changes. Although these traits were also present in some non-avian theropods, in surviving birds they combined with the ability to travel long distances to seek refuge and remaining resources in a fragmented and impoverished environment. After the impact and the most intense phase of the impact winter, the biosphere began a recovery process. Recent studies of marine microfossils indicate that certain forms of calcareous plankton reappeared and diversified over timescales of a few thousand years, suggesting remarkable ecological resilience once the basic conditions for photosynthesis were restored. On land, the pollen and spore record shows a succession from communities dominated by opportunistic ferns and plants, indicative of disturbed landscapes toward more structured forests and shrublands as the early Paleocene progressed. In this scenario of simplified ecosystems with many vacant niches, birds that had survived the crisis found opportunities to expand and diversify. The disappearance of their closest non-avian theropod relatives eliminated possible direct competition in certain insectivorous, small carnivorous, or omnivorous niches. At the same time, the absence of large herbivorous and carnivorous dinosaurs modified the structure of terrestrial communities, allowing other groups, such as mammals, to also experience significant evolutionary radiation during the early Cenozoic. From the first modern birds to the current avifauna, the living legacy of dinosaurs. After the K/PG boundary extinction, the first million years of the Paleocene show simplified terrestrial ecosystems with relatively low diversity and modest body sizes in most vertebrates. In this context, the birds that had survived belonging to the crown group neornithes began to diversify by occupying niches that had become vacant. The fossil record of the early Paleocene documents small and medium-sized forms, many of them with generalist, insectivorous or omnivorous habits, distributed in forests along water margins and in expanding open environments. From a phylogenetic point of view, neornithes is divided into two major branches, Gallo-Anserae, which includes the lineages that would give rise to galliforms and anseriforms, that is, chicken-like birds and duck and goose-like waterfowl, and neoaves, a diverse group that encompasses the rest of modern birds. Already in the Paleocene, early representatives of these clades can be recognized, although their external appearance and ecological adaptations do not fully match current forms. In many cases, the fossils show combinations of primitive and derived traits, reflecting a phase of evolutionary experimentation following the Cretaceous crisis. During the Paleocene and Eocene, Earth experienced generally warm climates, with episodes of pronounced warming such as the Paleocene to Eocene thermal maximum. High global temperatures and the absence of large polar ice caps allowed forests to develop at high latitudes and subtropical ecosystems to exist over extensive regions. Birds took advantage of these conditions, expanding their distribution into areas now considered temperate or cold, diversifying in dense forest environments, lake systems, coastal zones, and emerging archipelagos. During these intervals, recognizable lineages of aquatic and marine birds already appear, such as the earliest representatives of groups related to modern cormorants, gulls, and wading birds. Primitive penguins also appear, some of them large, indicating early colonization of cold marine environments in the southern hemisphere. Their anatomy illustrates the transformation of wings into flippers adapted for diving, with robust bones and joints capable of withstanding stress in an aquatic environment. These changes show how a single body plan derived from theropods could adapt to either aerial or aquatic locomotion depending on selective pressures. In parallel, the major lineages of terrestrial birds consolidated. Retites, that is, large flightless running birds such as ostriches, emus, and rheas and tinamous, represent neornithes lineages that evolved towards secondary flight loss or reduced flight capabilities, associated with cursorial lifestyles. On some continents, especially in the southern hemisphere, giant flightless birds developed, such as the so-called terror birds in South America, which during part of the Cenozoic occupied the role of large terrestrial predators. These forms demonstrate that after the disappearance of non-avian dinosaurs, certain bird lineages explored trophic niches previously occupied by large theropods. The diversification of neoaves intensified during the Eocene and Oligocene. In these periods, clades emerged that would lead to diurnal birds of prey, owls, cuckoos, swifts, hummingbirds, and numerous other families. The evolution of angiosperms, with increasingly diverse floras, stimulated the emergence of birds specialized in consuming nectar, fruits, and seeds, generating coevolutionary relationships between plants and pollinators or seed dispersers. The development of beaks with diverse shapes and sizes, whether long and slender, short and conical, robust for cracking seeds, or curved for tearing flesh, reflects this adaptation to differentiated food resources. From the Oligocene, and especially during the Miocene, the progressive expansion of open environments and savannas, associated with a slightly drier and more seasonal global climate, favored the radiation of birds adapted to open ground, such as many terrestrial granivorous passerines. Passerines, which today constitute the most diverse group of birds, appear to have experienced a particularly intense evolutionary burst during the Miocene, linked to the proliferation of herbaceous plants and grasses and the availability of insects in these new landscapes. Their complex vocalizations, ability to occupy varied microhabitats, and remarkable ecological plasticity partly explain their later success. During the Pliocene and Pleistocene, climatic fluctuations and glacial cycles added new selective pressures. Birds adapted to long-distance migrations, synchronized with seasonal changes in food availability and alternating cold and temperate climates at different latitudes. Dinosaur-derived physiology, such as a lightweight pneumatic skeleton, an efficient respiratory system with air sacs, and musculature specialized for flight, allowed many species to develop migratory routes spanning thousands of kilometers annually, connecting continents and oceans. During this same interval, the appearance and expansion of humans added a new and decisive factor. Hunting, habitat transformation, the introduction of predators on islands, and ecosystem modifications led to the extinction of numerous large birds, especially in island systems. Examples such as the dodo in the Indian Ocean, the moas in New Zealand, or the large flightless birds of Madagascar illustrate how lineages that were evolutionarily successful for millions of years can disappear in very short timescales under anthropogenic pressures. These recent extinctions mainly affected forms ecologically comparable to some non-avian dinosaurs, large or medium-sized flightless herbivores and specialized predators. Today, approximately 10 to 11,000 bird species are recognized, distributed across virtually all environments on the planet, from hot deserts to polar regions, including tropical rainforests, high mountain ranges, and open oceans. All of them retain traits inherited directly from their dinosaur ancestors. The presence of feathers, a bipedal posture with hind limbs as the primary support, the basic structure of the hip and ankle, calcified eggshells, the organization of the respiratory system with air sacs, and the arrangement of certain skull and neck bones. The current diversity of forms found in gliding birds such as albatrosses, diving birds such as mergansers and penguins, running birds such as ostriches, climbing birds such as woodpeckers, or acrobatic flyers such as swifts derives from modifications of this same basic body plan that originated in Mesozoic Coelurosaurian theropods. Each living species represents a surviving branch of a story that began with the first dinosauromorphs of the Triassic. From a phylogenetic perspective, dinosaurs did not go completely extinct at the K/PG boundary. They persist in modern birds, which today constitute the main living lineage of dinosaurs in the biosphere.